Today we're going to cover topic 2.4, which is exponential function manipulation. So it is essentially combining function transformations with our exponential functions, being able to determine how a function has changed, what did it do, how did it move, what is the new function that it's behaving like. Most of our manipulation is going to come from three major properties of exponents. The first being the product property, the second being the power property, and the third being the negative exponent property. So from our previous kind of schooling, so maybe when your first 2 or 3 years of high school, we talked about exponentials and the shortcuts involved with those exponentials. So a product property means if you have two of the same base and those are being multiplied together, then essentially you can keep the same base and simply add those exponents, and vice versa. So for example, if you had x to the fifth times x to the third, that would be like saying 5x's times another 3x's gives you a total of 8x's. Well, 5 plus 3 also gives you 8. And vice versa. If you knew that you had 8, you could split them up into 5 plus 3. You might also be able to split them up into x4 times x to the fourth. So any combination that gives you that 8, you could do x times x to the 7. So we're able to move back and forth depending on what information we're given and then what information we need. So for example, if you had 2 to the power of x times 2 to the power of 3, or 2 cubed, then you could say 2 and then add those exponents together, and that's what you would get here. Vice versa, if you knew that this is all that you had was 2 to the x plus 3, I could go and say, well, addition kind of translates to multiplication and vice versa. So if I'm adding x plus 3, then essentially I was looking at things that were being multiplied together, and that's kind of what we're going to be focusing on a lot on the back half of your notes. The same is true with something called the power property. So this one is when you have a base and an exponent and you raise that to another exponent. The shortcut says that you can simply multiply those exponents together. So for example, 5 to the power of x quantity cubed would be like writing x to the fifth 3 times. Well, that would be 1, 2, 3, 4, 5x is here. 5x is here. 5x is there. If I looked at all of them and I counted them up, I would end up with 15, the same way that 5 times 3 is equal to 15. And if we see x to the 15th, then we know, okay, that is 5 times 3, and multiplication translates to, a power, so we would say x to the 5th would need to show up 3 different times. So same thing here, my base is 2, my exponent is x, so it would be like writing 2x, 2x, 2x. So we would keep the base, so all of them have the 2, and then you would have 3 x's in total. Because you would say x plus x plus x, because multiplication translates to addition. X plus x plus x is 3x, or just multiplying your powers together. The one that gets people really confused is your negative exponent. A negative exponent is only about location. So every integer can be written as a fraction or as a ratio. So if you have the number 5, we know that we can just throw it over a 1, and now you have a ratio, you have a proportion, you have a fraction, you have a scale factor, whatever you choose to call that. A negative exponent simply means that we are moving locations. So if I had b to the negative n, and I needed it to look like a rational number, then I could throw it over the 1. Notice that the b to the negative n is in the numerator. Well, in order to get rid of that negative exponent, we would simply slide it down into the denominator, and make sure that our empty spaces are filled with a 1. So when we're looking at x to the negative 3, x to the power of negative 3, if I wanted a rational number, I could simply put it over 1. Notice that the negative exponent is only attached to the x, so the x is going to move from the numerator down into the denominator. When it moves, it becomes positive. This empty space, we do not want it empty, we fill it with a 1. If there was something already there, we would leave it alone. So 2 to the negative x, if I put that over a 1, notice it's in the numerator, it slid down into the denominator, gives me a rational fraction number. So it's using these, and vice versa. If I knew that it looked like this, then I could slide that up top, and when I slide it up top, that positive now becomes a negative x, and we're right back where we started. So we're going to be using these both in the forward and backwards direction today. So one of the things about transformations is that the same holds true about transformations regardless of what function we're looking at. So when we look here, earlier in Unit 1, we talked about function transformations with x being a liar. Anything that hangs out with the x is a lie. So whatever it looks like it's doing the opposite. So if I'm looking at the following function, I would say that this 2 is hanging out with my x. Well, the problem is that it's a liar. So it's not really a positive 2, it's a negative 2. And so if I asked you determine the horizontal transformation, which is what the instructions are asking us to do, determine the horizontal transformation of each of the following, well, then I know that originally I had f of x is equal to 4x, and then I moved it 2 units, not to the right. It looks like it's supposed to go to the right, but it's a liar, so it moves 2 units to the left. The same holds true here in example B. So if I look at this function, my 3x is dealing with any kind of horizontal transformation. 3 is being multiplied by x, which means that my figure should be getting either smaller or bigger, because it's multiplication and division are kind of inverse functions. So it's either going to get it's going to get proportionally bigger or smaller. So if I'm looking, I know that my original function is 2 to the power of x. And then I look at my scale factor, my dilation, my what I'm multiplying by. It is a liar, and so I'm going to take this function and dilate it horizontally, horizontal dilation, by not a factor of 3, but of 1/3, because anything that's doing business with that x is a liar. Same holds true with letter C. I'm looking at 9 to the x divided by 2. If you don't like the way that that looks, you are allowed to rewrite it as x over 2. I do know that this can be rewritten as 1/2 times x, so that you can kind of see all of the representations. Well, if this holds true, my original function would have simply been 9x. And now I have to address the 1/2. So I do know that it is multiplication, which means that that is representing a horizontal dilation. And since it is around my x, it is a liar. So instead of being dilated down by 1/2, it is being dilated by a factor of 2. So if I look at example D, there's another shift that's happening here. I'm looking at that x minus 1, which means that my original function would have simply just been 5 to the x. The minus 1 represents a shift. So we have a horizontal shift. It looks negative, but it's really positive. So we're going to take our original function, 5 to the x, and we're going to shift it right 1 unit. So we're taking those transformations that we have learned in Unit 1, applying them to exponential functions. The only difference is that all of my x values are hanging out in the exponent position. because it is an exponential function. But all of the transformations stay the same. Anything that's hanging out with my x is a liar. If it's being multiplied, that means we have a dilation. If it's being added or subtracted, it's just being moved. So what I want to do now is take a look at those product properties and I kind of apply those to our functions. So earlier we talked about whenever I have an exponent like x plus 2 or 4 to the power of x plus 2, I can rewrite that. So here's where I'm at in our notes, that front page. I can rewrite addition of an exponent as multiplication. So I do know that I had 4 to the x times x squared. And that's how we ended up with that addition sign in the middle, is that x plus 2 is because it came from an x, 4 to the x times another 4 squared. Well, if we clean this up, I can't clean up 4 to the x. I don't know what that is, but I do know 4 squared. That's going to give me 4 squared is 4 times 4, which is 16, 4 to the power of x. So we're saying that this transformation is equivalent to this function, meaning that even though they look different, if we were to graph them, they're going to end up in the same position on our graph. So when you rewrite an exponential function in this way, there's no longer a horizontal translation. So we're not having to look at a shift of any kind. We're just looking at a new, clean version of a function that happens to be mapped in the exact same location as the one that we originally moved in the first place. So every horizontal translation of an exponential function, so here's that horizontal, oops, my apologies. Here's that horizontal transformation in green. It's equivalent to a vertical dilation. So kind of rearranging things, and instead of, doing something horizontally, we take our original and we change our original vertically. So if I look at these, I am dealing with x plus 3. So in order to have an addition, that meant I originally had to have 2 to the power of x, and I had to multiply it by another 2 to the power of 3, because when you have the powers up here, that's when you can add them. So all we've done is separated them out, and now we're going to clean it up. Well, 2 to the power of 3 is 2 times 2 times 2, which gives me a value of 8. So if I wanted to rewrite this, I could say 8 times 2 to the power of x. I would end up with an equivalent function, and that would be f of x. We want to make sure we leave it in function notation. So we're really just looking at like a cleaner version of this. So instead of having these exponents that have weird stuff going on in it, we can now look at our clean version. You can tell me more about it. You can say, hey, this one had an initial value of 8. It was doubling every single time, over and over and over again. This represents exponential growth, and it's concave up. So once you have it in that exponential form, you can give me a lot more information. Let's try letter B. So this one has an exponent of x minus 2. Well, if addition represented, two quantities being multiplied, so let me squeeze this out. If when we were adding our exponents, we were using multiplication, now all of a sudden we're subtracting them. Well, subtraction is the inverse of addition, kind of the opposite. So what would be the opposite of multiplication? So I would be dealing with some division here. So I would be writing this one as 3 to the power of x over 3 squared. Some people might write it as 3 to the power of x times 3 to the negative 2. Well, now I'm just dealing with a negative exponent that maybe I wasn't ready to deal with in the first place, or maybe it's just an extra step. Both of them come out the same, because a negative exponent simply means I just need to put it in the denominator, or if it's in the denominator, put it in the numerator. I prefer to handle it first thing, because addition represents multiplication, subtraction represents division. Now I can say this is equivalent to 3x over 9. People want to do this and reduce. That's not possible because our numerator does have this exponent attached. But I do know that I can rewrite this as 1/9 times 3 to the power of x, which is exactly what we ended up with here. So I could say g of x is equal to 1/9 3 to the power of x. So we're just kind of dealing with the numbers and then letting the variables represent what they represent. So letter K, there's a lot going on here. This time we have an exponent of x plus 2, but look what it is attached to. That exponent has its own base, which means when I write this out, that 3 gets the x. Oops, my apologies. That 3 gets the x, and the 3 also gets the 2. You might be asking what's going on with the 4. The 4 is just a scale factor, so it's not attached to anything, it's not being shifted in any direction, so we leave it right where it is at. So when we clean this up, we have 4 times 3 to the power of x times 9. Well, I have like terms. So 4 times 9 is 36 times 3 to the power of x. We can't combine the 36 and the 3 because the 36 has no exponent and the 3 has an exponent of x. That is your variable, and we can't be going around trying to change variables up on things. So we're just kind of doing like cleaning math up. We're just cleaning it all up. So when we look at the back, now we're addressing the power property. So in the front, we were dealing with, when your x had something added or subtracted to it. Now we're going to have what's going on if you have x being multiplied by something. So let's take a look at this first one. Which of the following functions is equivalent form? So right now I have an exponent of 2x, which means that there's multiplication happening here. So I know that when I rewrite that, I need to set it up so that it's representative of multiplication. So I would need to have 9 squared written x amount of times, or that power property, because if you have a power raised to a power, then we have superpowers, which is multiplication. Okay. Well, if I'm looking at this, I can go in and say, I can do that. I know that. I can simplify that. 9 squared is simply 81 raised to the power of x. So if I look at my options, that looks a lot like option D. So knowing when to separate them using addition, subtraction, how that translates, versus separating them using multiplication and how that translates with our exponents. So let's look at our last one. Which of the following is equivalent to the form 9 times 4 to the x? Well, 9 times 4 to the x is already pretty clean. So let me go in here and look at my options. Okay. Well, if I look at the 9 doesn't have any exponent attached to it. It's not related to the 4 in any way. And so I know that that was probably my initial value to start off with. So if I look at my options, A and B are out because they're saying we're starting off with a value of 3. I don't have an exponent attached to the 9, so it's not like I can manipulate that in any way to reduce it down to a 3. So if I'm looking now at 16x divided by 2 and 16 times 2x, I'm looking at which one of these would essentially give me a 4x. So if I separated these out, this would be 16 times 1/2, or 16 to the 1/2 times x. This would be 16 squared times x. So whenever that multiplication is happening, here's where those I don't know why I keep calling them ordered pairs, the parentheses go. Well, anything raised to the 1/2 is the same as taking the square root. So 16 to the 1/2 is really like the square root of 16. 16 squared is 256, at least I hope. And it is. Well, the square root of 16 is 4 to the power of x versus 256 to the power of x. I need something that is going to be equivalent to what I have been given. And so there's the 4x from the original equation. So my answer choice is letter C. So it's really just kind of manipulating and rearranging and swapping out equivalent values based off of if you have exponents that are being added and subtracted versus exponents that are being multiplied.